Picture this. You're sitting in the exam hall, the air conditioning is humming, the clock on the wall is ticking incredibly loudly, and you're staring down at a real Cambridge past paper question. We've all been there, right? Today we are going to dive deep into exactly why students like Alex completely overload on raw facts, while students like Sam absolutely rush through and miss the command words entirely. Welcome to the Marathon Runner. Listen, taking a Cambridge computer science exam, it is absolutely not a sprint. It is a grueling, intense marathon of mental endurance, precise pacing, and strategic energy management. It really doesn't matter if you're currently building your foundational knowledge in syllabus codes like 0417, 0478, 0983, 0984, or 2210, or if you're gearing up to face the ultimate final boss, that is the 9618 AS and A-level syllabus. The core challenge you're facing remains exactly the same. You're in that seat, time is slipping away, and you are confronted with a complex, multi-layered scenario that demands way more than just rote memorization. It demands deep, structured, analytical thinking. Now, let's talk about our two typical students. First up, there's Alex. Now, Alex is brilliant at memorizing textbooks, literally knows every definition inside and out. But under the intense pressure of the exam, Alex just dumps all those raw facts onto the page without any actual analysis of the question being asked. And then we have Sam. Sam feels that immense time pressure, instantly panics, rushes through the entire paper, and completely ignores the command words that tell you exactly how the examiner wants the question answered. Throughout the course of this explainer, we are going to tear down and fix both of their deeply flawed approaches.
So, what is really going on here? The core challenge is interpreting things like NOR gate symbols and truth tables under intense, unrelenting time pressure. And look, according to the principal examiner reports, which are basically the examiner's secret diaries, this is the exact spot where candidates consistently bleed easy marks year after year. But you have to ask yourself, why? Why do smart students find interpreting complex binary representations so incredibly difficult? Well, it all comes down to cognitive load. It's like juggling. When you look at a complex logic circuit, your brain isn't just processing a simple shape printed on a page, oh no. Your brain has to simultaneously recall the precise textbook definition of the gate, trace the fluctuating binary inputs, calculate the literal causal relationship step by step, and then, just to make it harder, invert the output because of the not bubble on the NOR gate. That is a massive, massive amount of simultaneous processing happening in your working memory. Now, add the intense anxiety of a ticking clock, and that cognitive load becomes totally overwhelming. The juggling balls drop. Students completely forget to apply systematic analysis. Instead, they panic and try to just guess the final output by glancing at the whole circuit at once. They skip the rigorous, step-by-step decomposition that is absolutely required by the theoretical architecture of the Cambridge syllabus. And that's exactly where it all falls apart.
Let's look at this side-by-side comparison of how our two students handled this exact pressure. The specific question asks candidates to evaluate the use of a NOR gate in a specific automated lighting scenario. Okay, look at Alex's answer on the left. It is just a massive, intimidating wall of text, detailing the entire history of universal gates, drawing out the complete, generic truth table, and giving a perfectly accurate definition of binary logic. It's all factually true, it's great computer science. But here's the kicker. It contains absolutely zero analysis of the actual lighting scenario provided in the question. Because of that, Alex gets almost 0 marks. Now, look at Sam on the right. Sam sees the word NOR, remembers the panic of the ticking clock, scrawls output is 0, and frantically flips to the next page to save time. What did Sam do? Sam completely ignored the command word evaluate. Evaluation isn't just stating a fact. Evaluation absolutely demands that you consider alternatives, that you analyze real trade-offs, and most importantly, that you explicitly justify your decisions with evidence from the text. Both of these approaches, while totally different, represent a massive failure in energy management and exam strategy. They are sprinting blindly in the dark, instead of pacing their logical reasoning like a marathon runner.
So, what is the crucial takeaway here? It's that Cambridge examiners aggressively use the method mark strategy. They are actively looking to reward your analytical process just as much as, if not more than, your final derived answer. Look, if you take nothing else away from this explainer, remember this. Method marks are the absolute golden rule of Cambridge computer science. The examiners are not just mindless grading machines looking for the correct final binary digit. They are basically detectives. They are looking to see your procedural framework in action. They want to track your footprints. If a question asks you to extract data from a complex binary representation, perform cascading calculations, and draw evidence-based conclusions, the marks are sprinkled across that entire journey. Think about it. If you make a tiny, silly arithmetic error at the very last second, but your underlying method, your algorithmic thinking, and your logic gate cascading are all perfectly structured and clearly written out, you are still going to secure the vast majority of the marks for that question. Mastering the core principles means showing your work, You have to make your invisible thought process totally visible on the exam paper. You have to actively prove to the examiner that your conceptual understanding is robust enough to transfer to whatever unfamiliar context they throw at you.
Section 1. Mastery of core principles. Let's shift gears and look at exactly how mastering these basics builds a highly connected conceptual understanding.
All right, it is time to break down the ultimate secret weapon for dominating Cambridge exams, the PEAL framework. That stands for Point, Evidence, Explanation, Link. Now, before we dive into how exactly this transforms your grades, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to PEAL. Listen, this is absolutely not just some fluffy English essay tool. In computer science, it is a rigid, highly structured algorithm for answering high-level analytical questions. Think of it as code for your brain. Your point is your direct, punchy answer to the specific command word. Your evidence is the cold, hard data extracted straight from the scenario. For example, explicitly stating that input A and input B are both currently reading 0 in the provided truth table. Your explanation is where you get to flex your theoretical knowledge, clearly stating the rule that a NOR gate will output a 1 only when both inputs are exactly 0. And finally, the link. This is the magic part. The link connects all of that theory back to the specific real-world context of the question, concluding that, therefore, the physical security alarm will activate. Using this structured reasoning practically guarantees that you hit every single hidden requirement the examiner is searching for. It forcefully demonstrates that top-tier cross-topic connection that Cambridge examiners absolutely crave.
Okay, I want to challenge you right now. Start your 30-second mental timer and see if you can visualize how to apply this standardized 5-step processing sequence to the very next past paper you take. Step 1. Deconstruct the question. Literally take your pen and highlight the command word. Is it asking you to describe, to evaluate, or to compare? Those all require entirely different answers. Step 2. Extract relevant data. Pull the specific binary states, the variable names, or the boundary conditions straight out of that dense scenario block. Don't leave them behind. Step 3. Select your analytical framework. For most extended writing tasks, your framework is going to be PEAL. Step 4. Execute with clear, undeniable notation. This means drawing incredibly neat truth tables, using the formally correct Boolean algebra symbols, and clearly showing your step-by-step decomposition. Do not make the examiner guess what you meant. Step 5. Present with correct terminology. This is huge. Never ever write, "it flips the bit." That's casual talk. You write, "the not operation inverts the binary state." See the difference? By practicing this so much that this 5-step sequence turns into literal muscle memory, you drastically reduce your cognitive load during the actual exam. You no longer have to waste energy thinking about how to answer. You only have to think about what to answer.
Section 2. The Method Mark Strategy. This is the transformation phase, where precise algorithmic thinking literally turns those brutal red pen marks into beautiful green check marks.
Look closely at how this builds. The generic answer on the left gets absolutely nothing, 0 marks, while the perfectly structured PEAL answer on the right earns maximum method marks for flawless logical reasoning and cross-topic connections. Let's break it down. The generic answer, NOR gates output 0, is a classic, devastating trap. It totally lacks precision. A NOR gate doesn't always output 0. It outputs 0 when any input is 1, but crucially, it outputs 1 when all inputs are 0. More importantly, though, that generic answer completely ignores the scenario. The examiner is sitting there thinking, okay, but what does this have to do with the question? Now, the top-tier answer on the right applies the PEAL framework beautifully. It takes the theoretical truth table logic and evaluates it directly against the provided scenario, which in this case might be an automated temperature control system. It meticulously explains the causal relationships. It says, if the temperature drops below the set threshold, which we'll call input 0, and the manual override switch is turned off, which is also input 0, then the NOR gate processes those two zeros and outputs a 1, which physically triggers the heater to turn on. Do you see how powerful that is? When evaluating a logic circuit, systematically processing the inputs through each individual gate one by one and actually writing down those intermediary values on the paper is the pure essence of the method mark strategy. It visually demonstrates your evidence-based reasoning, and examiners will basically throw marks at you for it.
So, take a really good look at this computer science success blueprint. This right here is your exact roadmap to cracking those top grade boundaries. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's look at the blueprint. First, you must identify causal relationships. In logic gates or even in coding, this is literal, undeniable cause and effect. Input A explicitly causes output X. You have to state that clearly. Second, integrate with other syllabus areas. How does this specific piece of hardware logic actively impact the software efficiency? Showing that you understand how the whole system connects is huge. Third, you must prioritize analytical depth over superficial breadth. I cannot stress this enough. It is so much better to write 3 deeply analytical, intensely scenario-linked sentences than it is to write a full page of generic textbook definitions that don't actually apply to the specific question at hand.
Section 3. 3 Fatal Exam Mistakes. It is time for an interactive workshop. We are going to look at the top errors that consistently, year after year, destroy candidates' scores.
According to the official Cambridge Principal Examiner reports, there are exactly 3 fatal mistakes. Listen, these aren't just minor typos or little formatting errors. These are fundamental, catastrophic flaws in examination technique that occur across hundreds of thousands of papers globally. The examiners collate these massive reports every single year, and I promise you, every single year, the exact same 3 issues rise to the top of the pile. If you can focus your energy and eliminate just these 3 specific mistakes from your marathon strategy, you will instantly separate yourself from the average candidate pool and catapult yourself into the top percentile. It's really that simple.
I really want you to look closely at this list of examiner traps on your screen right now, and I want you to be honest. Try to find the flaw in your own previous exam papers. We've all done at least one of these. Trap number 1, using the wrong formula or algorithm context. This happens when you perfectly memorize a brilliant solution, but you blindly apply it to the wrong problem. For example, treating a complex XOR gate scenario exactly like a NOR gate scenario simply because the printed diagram looked vaguely similar when you were rushing. Trap number 2, forgetting boundary conditions in edge cases. In both programming and in logic circuits, the real test is what happens at the extremes. What actually happens when all inputs are flipped to 1 simultaneously? If you don't actively test those edge cases in your written answer, your evaluation is considered totally incomplete. Trap number 3, writing generic answers that completely ignore the scenario. We have talked about this, but it absolutely bears repeating because it is by far the most common way to bleed points. If the question asks you about a self-driving car's sensor array, and you just write a paragraph about abstract binary states without ever once mentioning the car, the road, or the sensors, you will score 0. Period.
The examiner commentary we are looking at here is totally ruthless, but honestly, it's fair. If you don't test thoroughly and explicitly evaluate performance in your answer, you just lose the points. Let's analyze this table together. A student confidently writes, "The algorithm loops 10 times." Seems fine, right? Wrong. The examiner marks them down severely because they missed the boundary conditions. Does the algorithm loop from index 0 to 9, or does it loop from 1 to 10? What exactly is the termination condition that breaks the loop? That tiny lack of precision is deadly in computer science. Now look at the second snippet. The student writes, "NOR gates are universal." Well, hey, that is a perfectly true statement. You can technically build any other logic gate in existence using only NOR gates. But look at the examiner commentary. It notes that this is a completely generic statement. It wasn't specific to the context given. The question didn't ask about the theoretical universality of gates. It asked why a NOR gate was specifically chosen in this circuit design to lower manufacturing costs. Again, context is absolutely everything.
This quote directly from the Examiner Alert is your absolute golden rule. Read it with me. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. All right, we are going to start a 30-second speed writing challenge right now to craft one perfect context-linked PL paragraph in your head. Ready? I want you to imagine a 6-mark question asking exactly why a NOR gate is utilized in an automated greenhouse window system. Go. Think about it. Your point needs to explicitly state the function of the gate. Your evidence needs to pull directly from the greenhouse scenario. So you better be talking about the temperature sensor and the humidity sensor. Your explanation should define exactly how the NOR logic processes those 2 specific environmental inputs. And your link must definitively, clearly state whether that physical window opens or closes based on that finalized logic. If you can train your brain to write that tightly, that clearly, and that specifically every single time, you are truly mastering the method. You are proving your analytical depth beyond a shadow of a doubt.
Section 4. Comparative Analysis Mastery. Moving into our final system, we absolutely must tackle those higher-order assessment objectives that demand deep evaluation of alternatives and heavily justified recommendations.
To truly master comparative analysis, you must explicitly identify both similarities and differences, and you must use specific comparative connectives to bridge your evidence together. Listen, when you finally get to the back of the paper, to those massive 8 to 12 mark essay-style questions, you cannot just list the cool features of System A in one paragraph and then list the features of System B in another paragraph and just cross your fingers hoping the examiner connects the dots for you. They won't. You must do the connecting for them. You need to forcefully use words like whereas, conversely, similarly, and in contrast. Let me give you an example of a perfect sentence. System A uses purely hardware-based NOR logic resulting in significantly faster processing speeds, whereas System B utilizes a software-based algorithm which introduces slight processing latency but offers far greater flexibility for future system updates. Boom. That one sentence explicitly evaluates relative importance, it focuses heavily on trade-offs, and it perfectly uses a comparative connective. That is a maximum mark sentence.
By meticulously following this procedural framework every single time, you ensure that every single step-by-step decomposition and every single binary calculation is fully verified before you move on. Let me highlight the most ignored step here. Never, ever skip step 4, verify results. Once you have written out your massive truth table or traced your complex algorithm, you need to run a test case through it mentally. Stop and ask yourself, did you actually hit the boundary conditions? Did you account for the weird edge cases? If you were designing an algorithm from scratch, dry run it with a totally extreme, unexpected input value just to see if your logic breaks. This rigorous, disciplined testing phase is exactly what separates the frantic candidates who rush, like our panicked friend Sam from the beginning of the explainer, from the elite candidates who manage their time and their cognitive energy effectively throughout the entire marathon.
These 3 rules right here represent the ultimate cheat sheet for mastering the grueling marathon that is the Cambridge Computer Science exam. Let's recap them. Number 1. Command word decoding. Never ever answer a describe question with a simple bulleted list, and absolutely never answer an evaluate question without offering a highly justified evidence-based conclusion. Number 2. Peel framework application. You must structure every single analytical response with a clear point, evidence, explanation, and link to absolutely ensure you are anchoring your theoretical knowledge directly to the real-world scenario. Number 3. The time management matrix. You have to strategically allocate your precious time strictly based on the method marks available. Do not waste 10 minutes writing a beautiful generic introduction for a measly 3-mark question, and definitely do not rush a massive 10-mark comparative analysis in the final 2 minutes of the exam. You have to pace yourself.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Think about what that actually means. Moving from a frustrating C to a solid A, or bumping a B up to that coveted A star, isn't about suddenly waking up and becoming a certified genius at binary mathematics overnight. That's a myth. It is purely 100% about systematically refining your exam technique. It's about ruthlessly eliminating those fatal examiner traps we discussed, and it's about learning how to communicate your deep theoretical understanding in the exact, highly structured format that the rigid Cambridge rubric demands. It's a game. And now you know the rules.
We have covered a truly massive amount of ground today, from managing the intense cognitive load of cascading NOR gates to mastering the elegant structural simplicity of the Peel framework. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. The very next time you sit down with a past paper, I want you to remember this explainer. Don't be an Alex who just overloads the page with generic, untargeted facts, and definitely don't be a Sam who panics and rushes past the critical command words. Be the strategic marathon runner. Deconstruct the scenario calmly, verify your edge cases rigorously, secure every single one of those method marks, and show the examiner exactly what they are desperately looking for. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep pacing yourself, keep analyzing, and I'll see you in the next explainer.